Okay, welcome back. Time to finish our discussion on charge. We talked in the last video about how we can quantify amounts of charge. We can either describe charge in terms of elementary charges, which is basically counting up the difference in the number of electrons and protons and stating that as the charge. Or we can talk about charges in coulombs, which is a term for a whole bunch of charges altogether. 1 coulomb is 6.25 times 10 to the 18th elementary charges. Now, most large objects, we're lucky that this is the case. Most large objects are what we would call electrically neutral. And this is good for us, because otherwise you would be getting shocked no matter what you touched. I know it feels like that in the winter, like you're getting shocked no matter what you touch, but we're talking like this is, on average, most objects are electrically neutral, meaning they have equal numbers of protons and electrons. Okay? So neutral objects, it's not that they have no charge, it's that they have equal numbers of protons and neutrons. Now, not all objects are electrically neutral. Some objects have what we call a net charge. And an object gets a net charge by either gaining or losing some of its electrons. Remember, it has to be the electrons. Protons are kind of locked in place. They're in the nucleus. They're in the center of the atom. They're not going anywhere. They're very tightly packed in. Electrons, on the other hand, can move about depending on the material fairly easily. Okay, definitely easier than protons can. So, when electrons are transferred to or taken away from an object, that leaves it with a net charge. It leaves it with an imbalance in the number of electrons versus the number of protons. Remember, this doesn't tell you how many electrons or protons there are on an object, it just tells you the difference. In other words, it tells you how much extra charge of one type there is. It'll either tell you how many more electrons there are than protons or how many more protons there are than electrons. So, let me give you a quick example showing how an object could get charged. I'm going to draw this very quickly. Here is a comb. This should be a familiar example for some of you. Okay, not a very good comb, but whatever. And here is a person. And the person's got some hair. That's kind of key for this. Now, the comb and the person are both large objects, okay? They contain, I don't even want to talk about how many electrons and protons they contain, but they're both typically going to be electrically neutral, meaning same numbers of protons and electrons. Now, I'm not going to draw all those protons and electrons. I'm only going to draw a select few just to represent what I'm talking about here. And I'm going to symbolize, and this is going to be very common, I'm going to symbolize protons as pluses, electrons as minus signs. So protons are positive, they get plus signs. Electrons are negative, they get minus signs. So if we look at the comb right now, I have 1, 2, 3, 4 pluses, 4 protons, 4 positive charges, 1, 2, 3, 4 electrons, negative signs, minuses. The charge of the comb right now is 0. 0 elementary charges is the net charge. I should say the net charge. Obviously there are charges, but they are balanced out. There's equal numbers. Let's start with equal numbers on the person as well, on their head. Obviously I'm not drawing them right on there, but you get the idea. 4 positive charges, 4 protons, 4 negative charges, the electrons. The charge on the person's head is also 0. Now what happens if the person goes and rubs their head or runs the comb through their hair? Okay, some of you who do this, who have to comb your hair, you will know what this does. Okay, especially in the winter when things are rather staticky. Running a comb through your hair often seems like it makes your hair a little bit more staticky than normal. Can make your hair stick up a little bit. The reason for that is because you are literally transferring charge from one object to the next. What the comb actually does is it pulls some electrons away from your head. So here's what that might look like. Remember, the positive charges will not move. Okay? They are locked in the nucleus. So I'm not going to change the position of any of the plus signs. I'm going to put them approximately where they were last time. However, the negative signs representing the electrons, those can move around. And they do move around, and they will move around. The comb actually pulls some electrons away. I'm not going to take all of them away, but I'm going to take some of them away. We're going to leave the head with 2 electrons, but the others are going to go to the comb. The comb literally just kind of picks them off the hair and goes. So now let's look at the charge on the comb. I still have 1, 2, 3, 4 positive charges, 4 protons, but 1, 2, 3, 4, 5, 6 negatives. So what would the net charge be? Remember, the net charge is the difference in how many electrons versus how many protons. 6 electrons, 4 protons. The net charge on the comb is negative 2e. Okay? So negative 2 elementary charges. Negative because there's more electrons than protons. 2 because there's 2 more. What about the head? Well, 1, 2, 3, 4 protons and only 1, 2 electrons. The head has a charge of positive 2e. So notice that's actually pretty interesting. Whatever the head lost in electrons was gained by the comb. We have this idea of conservation of charge, which we will build up later on in probably the next set of videos. Let me give you another example, and this is one that you can do at home. A neutral piece of Scotch tape is placed on a desk and is peeled off, taking with it 6.2 times 10 to the 13th electrons. What are the new charges on the tape and the desk? Okay, so we start with a neutral piece of Scotch tape. It gets put on the desk, and when it's peeled off, it takes with it this many electrons. So the tape gains 6.2 times 10 to the 13th electrons, and therefore it becomes negative. The desk loses the same amount. If the tape took those electrons, they didn't just pop out of nowhere, they came from the desk. The desk lost the same amount of electrons, and therefore it is now positive. Now, I could say that the charge of the tape is negative 6.2 times 10 to the 13th e, and the desk has a charge of positive 6.2 times 10 to the 13th e, but let's get the charges in coulombs. How do I convert from the number of electrons, the number of elementary charges, to coulombs? I simply do this. 6.2 times 10 to the 13th e for elementary charges is how many extra electrons the tape now has. Let's convert using one of the conversions from the front. And you can look this up on the reference tables. 1 elementary charge is 1.6 times 10 to the negative 19th c. So all I'm going to do, and it's very important that you understand how to use your calculator here, 6.2 EE13 times 1.6 EE negative 19, and I end up with this, 0.0000992. If I move that decimal, 1, 2, 3, 4, 5, 6, 9.92 times 10 to the negative 6 coulombs. That is the amount of charge. That is the difference in charge, or excuse me, the amount of charge represented by the difference in electrons and protons on their two objects. So what this ultimately boils down to is the tape, since the tape is negative, now has a charge of negative 9.92 times 10 to the negative 6 coulombs, and the desk now has a charge of positive 9.92 times 10 to the negative 6 coulombs. Okay? And this is kind of neat. I can prove that the tape now has a negative charge. Hopefully this works. Okay, let's not use that. Let's use this one. Okay. So I have a piece of Scotch tape right here. I'm going to get another piece of Scotch tape right here. And you'll see that right now, they don't really affect each other all that much. Okay, they're just kind of chilling. Okay, what I'm going to do is I'm going to put both of them on the desk. Okay, so off here, I'll move it like this. I'm going to put both of them on the desk. Hopefully I'm able to peel them off. Just cut my fingernails, so we'll see. Okay, so they're both on the desk. Now I'm going to peel them off. There's one. There's the second. And this is going to illustrate something that will be important in a little bit. If I bring the pieces of tape near each other, no, they weren't supposed to do that. Look how much one of them is affecting the other one. It's bending like almost all the way backwards. Okay? So, and then every once in a while they jump, and I still don't know why they do that. They're not supposed to. But anyways, you can see that they're really repelling each other now. What that's supposed to show you is that they both have negative charges. They both took electrons off of the desk. Now, in the winter, that demonstration works a little bit better because things are a little bit more staticky, but whatever. We're seeing that we can prove what sort of charge something has based on how it interacts with other objects that have charge. And we're going to get to that in just a little bit. But before we get to that, let's practice finding amounts of net charge. So, 4 objects have acquired different net negative charges. How many more electrons than protons does each object have? So A, the net charge is -8 times 10 to the -19th coulombs. We want to know, based on this net charge, how many extra protons or how many extra electrons does this object have that made it have that net negative charge? This is actually pretty easy to figure out. You simply take 8 times 10 to the -19th coulombs and you convert into elementary charges. Okay, we know that one elementary charge is 1.6 times 10 to the -19th coulombs. So basically, we know how much extra charge there is. We want to know how many elementary charge, or what this charge, the size of this charge, the magnitude of this charge in elementary charges, because that will be how many extra electrons there are than protons. 8, nope, -8. Raised to the -9 times 10 raised to the -19th divided by 1.6 e -19, we get -5 e. That tells us that there are 5 extra electrons on this object causing that net negative charge. Now, if you want, you can use the other conversion, 6.25 times 10 to the 18th e over 1c, and you should get the exact same thing. I'll prove it. -8 e -19 times 6.25 e to the 18, you still get -5. So now what we're going to do is we're going to find these net negative charges, and you can watch this happen. Okay? You can even do some of these on your own. 2.56 times 10 to the -18th coulombs. We're going to convert that. 1e, 1.6 times 10 to the -19th c. Equals -16e. That means 16 extra electrons. -1.28 times 10 to the -13th c. 1.6 times 10 to the -19th c. 1e. Okay, this one's pretty big. This amount of net charge is the result of 800,000 extra electrons. Okay, so notice, if we had positive net charges, that would have told me that I have more protons than electrons, not more electrons than protons. This last one is very important. Okay, it's a really, really important case. We're going to convert the same way we have been, -2.4 times 10 to the -19th coulombs, 1.6 times 10 to the -19th coulombs, 1e. You'll notice I get -1.5. This is different from all the other answers, e. What this would mean is that there's 1.5 extra electrons causing this net charge. But you're going to immediately cross that out because this is physically impossible. It is a law of nature that you cannot split an electron into some fraction of an electron, okay? You can't have a fractional charge for an electron. It just can't be done. You can't, an electron is one of the smallest bits of matter possible. You cannot subdivide it anymore. There's a limit to how much you can divide things. An electron is what we would call a building block. It literally, you cannot get smaller than an electron, okay? There's nothing inside of it. An electron is just an electron. Therefore, if you have a certain amount of charge, okay, such as the charge of an electron, you can't have a fraction of that because that would be like having half of an electron, and that just doesn't exist. I'm not saying we've never seen it. I'm not saying that like we don't, you know, that it could happen, but we're not technologically advanced enough. It does not happen, okay? So, all that being said, with the exception of some things that are inside of a proton or inside of a neutron, which we will talk about at the very end of the year, we're not there yet, objects can never have a non-integer number of elementary charges. Okay? Non-integer number. Integers are like your counting numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, and the negative numbers as well. So, objects can never have a non-integer number of elementary charges because that would imply that there is a fraction of an electron or a fraction of a proton hanging around somewhere, and that just doesn't happen. There is no such thing as half an electron or any other fraction of an electron. Okay? It does not exist. It's either a whole electron or nothing. Okay? Just like if you're counting the number of people in a room, you can't have a half a person in the room. Either a person's in the room or they're not. Okay? Or the population of the world. Either there's a person or there's not. It's 1 or 0. Okay? You can't have like half a person. So, non-integer number of elementary charges. Now, how do you know that? It has to be an elementary charge. You'll notice that, like, you might say, well, 2.56, that's not an integer. How is that possible? That is measured in coulombs. Notice that when we convert it to elementary charges, it came out to a whole number, to an integer. It's when the amount of charge in elementary charges is not an integer that cannot possibly happen. Okay, that's the rule for that. Now, lastly, we're going to talk a little bit about what we just did with the Scotch tape, how objects with electric charge interact with each other. It's very similar to magnets. If you know the rules for magnets, you know that like poles repel, opposite poles attract. We'll talk about magnets at the end of this unit. It's very similar for electric charges. If you have two positive charges, okay, like two protons, let's say, they will repel each other. If you have two electrons, they will repel each other. And if you have two neutral particles, like a neutron and a neutron, well, they do nothing. On the other hand, if you have a positive and negative charge, like a proton and an electron, they will attract to each other. The tricky one is what happens when you have a neutral object and a positive object, or neutral and negative. Now, you might be tempted to say that nothing happens because one of the charges is, well, 0. It doesn't have a charge. But I want you to think about what happens when you do that trick where you take a latex balloon and you rub it on your sweater or you rub it on your hair, and then you go next to someone else. You can make their hair stand up. Now, the balloon is charged. One of the ways to charge something is to rub it on an object. It will either gain or lose electrons. I think the balloon gains electrons, so it becomes negative. So you've got this negative balloon, and you go over to a person that has not rubbed up against anything yet. They are neutral. But if you put the charged balloon near their neutral head, what happens? The hair starts to stand up. So what's happening is the balloon is attracting parts of that negative object. If you have a charged object and a neutral object, they actually attract one another. And hopefully we'll get to see in class a little bit stronger of a demonstration than the two pieces of Scotch tape repelling each other. And hopefully they don't jump together like they did. Sometimes that happens, and I don't exactly know why. It must be some sort of Must be something with how I'm taking the tape off, or like the charge disparities on the tape. Maybe it's not centered or something. But in any case, the two pieces of tape, you could see that they were kind of repelling each other somewhat. They were both negative because they gained electrons, therefore they repelled each other. Okay? Negative and negative repel, positive and positive repel. So as a conclusion, we can write that like charges repel, opposite charges attract. They want to be close together. Repel means they want to be farther away from each other. A charged object and a neutral object actually attract each other. And finally, neutral and neutral have no effect. They do nothing. There's a nice summary of how charged objects interact with each other and with non-charged objects. When we come back, we will be spending some time talking about how to charge objects in the first place. Okay, but this is a good base for just knowing about electric charge, these notes. Let me know if you have any questions, and I will see you shortly.